Well, greetings, mathletes, and welcome back. We're going to be talking about the complex numbers today. Now, the complex numbers are kind of interesting because they were really born out of this idea of taking a square root of a negative. It turned out that these things were popping up quite often when they were trying to solve polynomial equations. Um, Initially, they were dismissed as not being anything, right? You can't take the square root of a negative. But over time, they realized that if you make some assumptions, um, you actually form an entirely new number system using the square roots of negatives, and that number system is called the complex numbers. And since we are going into a chapter on polynomials and solving polynomial equations and whatnot, we're going to need the complex numbers. So today is going to be just kind of a quick rundown. Hopefully you've seen these before, but if you haven't, I am going to be covering pretty much everything we need to know as far as the complex numbers go. So let's go ahead and get started. Okay, so the first idea here is, what do you do when you want to take the square root of a negative? Oops. There. No. There. Okay, square root of a negative. Like, for instance, the square root of negative 81. If it was positive 81, we could say the root is 9, right? But this is a negative 81, and that's a problem. Because the only way you can multiply two numbers to get a negative that we know of so far is multiplying a positive number times a negative number, in which case then it's not a square root. So this is how it ends up being handled. What we can do is peel off the negative. So I'm going to look at the positive square root of 81 times the square root of negative 1. Now, rules of roots mean that we can just multiply the radicands to get this back. So you can actually split up a root over its factors. And then we just kind of step to the side and think to ourselves, well, you know what? I can do this with any negative radicand, right? So any negative number that's in here, I can always peel off a negative 1 to get rid of it. So it's really convenient to not have to write the square root of negative 1 each time. What we're going to do is we're going to give it a name. And the square root of negative 1 we are calling I. Okay? I believe I was chosen because it was called the imaginary number. At least that's what I was told. It doesn't really matter as long as you remember that I is the square root of negative 1. What that does is that means that this is now the square root of 81 times I. Don't make the mistake of writing square root of I. I is not negative 1. It is the square root of negative 1. So at this point, all I have to do is take the square root of 81, and that gives me a 9. And so I can say my answer is 9I. It's 9 times the square root of negative 1. So in a lot of ways, this is a radical expression, because really what this means is this. Right? For the most part, though, we're going to be I is going to behave like a variable. So we're going to kind of treat it as such. Although it is not an unknown quantity at all. We know exactly what I is. It's just easier to compute using the symbol rather than the square root of negative 1. Now, you're probably asking yourself, what do you do with things that aren't perfect squares? Well, we have an answer to that. So if I have something that looks like, let's say, the square root of negative 12, right? What I'm going to do is I'm going to go ahead and pull, pretty much you can shorten all this stuff I just did, you can shorten it to popping its eye out. Anytime you see a negative here on a number, you can get rid of the negative by doing this. You can pull an I out. I know it sounds painful. And just write the positive root. Then once you have the positive root, you can just go ahead and use a factor tree or however you want to find this, simplify this root. Let's see, you got a pair of 2's there. So this is now 2I times the square root of 3. Right? Notice how I wrote it also. This is a pretty normal way to write these. I do happen to know that the homework program you are using would actually rather see this in a lot of cases. it wants to see the I at the end. So you can keep this number as a single unit. So you would write the I at the end. I believe that's what they're talking about. This is what's called the standard notation, right? In fact, we should define that a little bit better. Let's see here. Let me go ahead and do this. The standard notation for a complex number looks like this. It's A plus BI. So I have, this is called the real part. And this BI, or actually B, is called the imaginary part. And they basically form all of the complex numbers. A and B can also be 0. So if B is 0, you get just a plain real number. And if A is 0, you get a pure imaginary number, like 9i, or, well, actually, even this is a pure imaginary number over here, because I just have B is 2 root 3. So the standard form is when you actually have them physically separated out. So if I have something like this, that is not in standard form. To put it in standard form, what you do is you break this up over that fraction. So it would be 2/5, that's the real part, plus 3/5 I, and this would be the imaginary part. And so you can break complex numbers up into their real and imaginary components. That's actually going to be really important for those of you who are going to be climbing the calculus ladder. That's one of those things. There's a lot of cases where all you care about is the real part, and there's cases where all you care about is the imaginary part. So being able to separate them is actually important. Okay, so that's simplifying them, right? They're basically normal roots. You just, if you have if you're taking the square root of a negative, you just pull an I out to get rid of the negative. That's the basic idea. Now, this idea does seem strange because this is not a number. This isn't a real number. It's not a number that's on our number line at all. So it is something new, but as long as you get some practice and learn how to handle it, it's actually not a big deal. So let's go ahead and look at the next thing. So let's suppose we want to add. So we're going to look at addition and subtraction. And this is where they start actually behaving a lot like polynomials. So if I have two complex numbers, let's say I have 3 plus 5i, that's one complex number, and I want to add it to 6 minus 4i, right? Well, your gut probably tells you that you should just add the 3 to the 6 and the 5 to the 4, to the negative 4. And that's exactly what you do. You can, until you simplify these things and get down to it, you can really treat the I a lot like a variable. So you can think of these as collecting like terms. Really, technically, you're collecting like radicals because I is a radical expression. But yeah, we just collect our like things together. So the 3 goes with the 6, and the 5 goes with the minus 4, and we can just put those things together. 3 plus 6 is 9. And then 5 minus 4 is 1, so that means it's plus 1i. Oh, that's not a very good color. Let me just do it this way. I'll just rewrite it. So I end up with 9 plus i. So the real portion is 9. The imaginary portion is 1, right? There's always a 1 next to those things. And it's right. Yikes. It's right there. You can't see it, but it is there. You just don't need to write it. Okay. And similarly, probably the one thing you need to watch out for when subtracting these things, right? If I have something like 4i minus 3 plus 7i, You want to remember when this is subtraction that this distributes all the way across. So this is now 4i minus 3 minus 7i. And then I can just collect everybody together. You always want to write it so the real part comes first. So the minus 3 comes first. And then I have to see what I get here. 4i minus 7i is minus 3i. So it's minus 3i. And this would be the solution to that particular addition problem. Honestly, this is about as much as there is to adding and subtracting complex numbers. It's just a matter of matching up the terms, right? So you add the real to the real, and then add the imaginary to the imaginary. And that gives you your new real and imaginary values. Okay, so I want to look at multiplication now, and then I'm not going to pair it with division, not directly, because they really do feel like two different things when we're dealing with complex numbers. So let's look at multiplication first. Okay, now in multiplication, this is actually where it becomes a little bit more important to remember that I is equal to the square root of negative 1. Because what's going to happen when we multiply complex numbers is we end up multiplying an I by an I. And so what we end up with is an I squared. Now, I squared does get confusing to people. What you want to remember, it's an immutable truth, and sometimes it's even given as a definition of I, is that I squared is equal to negative 1. I is the number that when you square it, you get negative 1. So if you square it, you better get negative 1. And you can think about it this way, right? If I is equal to the square root of negative 1, well, if I square both sides of this, what happens to squares and square roots? They kill each other, right? So that leaves me with I squared. Since I peeled off that root there, I get negative 1. So it does work. Now, when we're multiplying, we are going to come across these things. So I just want to point it out. The best thing to do is just accept it. I squared equals negative 1. You should be mumbling that in your sleep. So let's take a look at something. So let's say, in fact, I want to look at these. So we put a regular polynomial. Let's say I have 3x times 4 plus 2x, right? And then over here, I'm going to do it with complex numbers. Instead of an x, I'm going to put an I. So we'll get 3i times 4 plus 2i. I just want to show how these are very similar, so you can actually use the things you know about multiplying polynomials to multiply complex numbers. So here, your gut should tell you just distribute, right? So that gives me 3x times 4 gives me 12x. And then 3x times 2x gives me 6x squared. Okay? Now, if we're dealing with polynomials, we're actually done at that point. Let's look at what happens with the complex numbers. Same thing, we're going to distribute. This gives me 12i, right? It's an I instead of an x. And then here, 3i times 2i gives me 6i squared. Now, I squared is negative 1, which means that I can take the I squared out and rewrite this way. 12i plus 6, and the I squared's gone. I'm going to put a negative 1 in here, because that's actually what I squared is equal to. So that gives me 12i minus 6. Now, while this is numerically correct, it's not technically done. The standard form puts the real part first. So you just need to swap the positions here, right? Because that put the imaginary part first. We just need to put it second. So the answer here should be negative 6 plus 12i. Okay, so let's just look at what we did. Okay, so as far as the first step goes, the actual multiplication, we just follow the normal distribution rules, right? So if I have two binomials, I'm going to FOIL, or whichever acronym you use to remember how to distribute two binomials. And then you have to go back through and look for I squareds, and that's really the only difference. Um, Other than that, they multiply exactly like polynomials. It's just a matter of dealing with the I squared. Okay, so let's take a look at another one here. All right, let's say I have 3 plus I times 3 minus 2I. Okay, now you treat these exactly like you treat polynomials. So let's see what you can do with it. Why don't you go ahead and pause here and just take a stab at what you think you're supposed to do. And then once you finish that, go ahead and push play and watch the rest of the explanation. And let's see, and we'll see if you're right. Okay, so I'm assuming you've already paused it here. Let's see. So, oh, I put that too high. I wonder if I can just do this a hair. That'll work, kind of. All right. So we need to distribute this. So that means I go 3 times 3. That gives me a 9. 3 times minus 2i, which gives me minus 6i. 3 times I, which gives me plus 3i. And then I times minus 2i. So that gives me minus 2i squared. There's that I squared again. It always pops in there. Now, what I want you to get good at, because it's going to save you a lot of time, is you may have to write that -1 in the first few times you do it. But really, what I want you to be able to do is recognize that whenever you have an I squared like this, it's just going to change this sign. So the next line should be 9 minus 6i plus 3i. And this I squared disappears and the sign changes. That's going to be a plus 2. Now, if you don't see why it got there, I have a minus 2 times I squared, which is -1, which gives me a positive 2, right? And so that's how I got that positive 2. But this part I committed to my head. So from here, it's just a matter of collecting like terms, right? We just need like radicals together. So 9 plus 2 is 11. -6i plus 3i is minus 3i. And we're already in standard form, so that's our answer. So that's not too bad. It's actually kind of fun. You can go home, show your friends. And, hell, this is on YouTube. You can bring your phone right to them, show them the whole thing. Okay, so let's take a look at one more. And this one actually has kind of in fact, let's make it 2 more, because they have a similarity between the 2 problems that I want to point out. So let's look at the next 2 problems here. So let's say they are 5 plus 2i times 5 minus 2i. And then the other one I want to look at is, let's do 9 plus I and 9 minus I. All right. So, yeah, go ahead and pause here and see if you can multiply these out, and then let's see what you get. Okay, I'm assuming you've paused it now. So let's take a look. So again, we're going to FOIL this whole thing out. All right, 5 times 5 is 25. 5 times minus 2i is minus 10i. Let's see, 2i times 5 is plus 10i. And 2i times minus 2i. Now, this is where I try to get you guys to start doing this in your head a little bit. That gives me minus 4i squared. The I squared makes it a plus 4, right? So just so you know, that last thing was ended up being a minus 4i squared, which ended up giving me a positive 4. Now I just need to collect my like terms. Well, minus 10i and plus 10i kill each other. And I end up with 25 plus 4, which is 29. Notice that has no imaginary component. I mean, it does, it's a 0. But that is a pure real number. And it's kind of interesting that that just happened. Let's look at the other one. Okay, notice this is actually a similar pattern. I have plus and minus the same values. I had plus and minus the same values over on this one too. So now, if we FOIL this one out, let's see, 9 times 9 is 81. 9 times negative I is minus 9i. I times 9 is positive 9i. And negative I squared is plus 1. Right? Because that's a negative I squared. I squared is negative 1, so that makes it a negative 1, which makes it a plus 1. Okay, but notice I just automatically just switched the sign because I knew I had an I squared in there. So that may take some practice before you feel comfortable just doing it. But no, that is where I'm trying to push you guys. So over here, again, these guys die, and I end up with 82. Again, a perfect real number, right? It's a pure real. It has a 0 imaginary component, so I don't have to deal with the I. It's kind of an interesting property, really. Let me show you why it works. Right, really what's going on is we're using this pattern. Right? That's the pattern we're using. The difference is, though, because there's an I in here, right? There's an I with the Y. Let's see what happens when it's an imaginary number. So I have x plus iy and x minus iy. What I end up with, and I'm just going to use this pattern, that's going to give me x squared minus iy squared, right? So that gives me x squared minus I squared y squared. Well, what's I squared but negative 1? So that means that makes it a negative 1. That turns this one to positive and gives me an x squared plus y squared. Okay, so this is a shortcut. This is actually a really nice shortcut. Let me switch colors here so I can make it stand out. If I have x plus iy times x minus iy, what I get is x squared plus y squared. Now, let's see if we can actually apply that to what we just computed. Let me get some of this off of here. Okay, so if I have, let's see, yeah, I'm black. 5 plus 2i times 5 minus 2i. Okay, you notice that the y squared doesn't include an I, right? So it's just taking the number part of this. Let's see how this works. Is it true that this is 5 squared plus 2 squared? It's 25 plus 4, which is 29, and that matches, right? That completely matches up. And notice you can do the same thing with over here. 9 squared is 81, that's this. And then plus 1 squared, which is right here. Again, the middle terms cancel out, and we get the whole thing. And we can use that shortcut, right? We can just square the 9, and then the coefficient of I in this case is 1. So we square the 9, square the 1, add them together, boom, we're done. That was not supposed to be a rhyme, but I'm okay with it. Okay, so let's take a look at the next thing. I'll be using that shortcut as we go through because we actually need these. We need this pattern to do division. I think I've mentioned it before, and hopefully it's been mentioned in other classes, that whenever you have, even with roots, But whenever you have a plus bi and a minus bi, right? These are complex conjugates. And one of the things about complex conjugates is that whenever you multiply conjugates, you always get a real number, right? You get a number that is devoid of an I. So it's actually important when I multiply these two things, right? I end up with a squared plus b squared and no I. That always happens. Actually, the solutions to the quadratic equation always come in conjugate pairs, right? They come with, they always have a, that's where that plus and minus actually plays in the quadratic formula when we see it, is because you get one plus for one conjugate and the minus for the other conjugate. So it's really kind of interesting. Okay, so let's look at division. Now, division is really a process. When it comes to complex numbers, division is rationalizing the denominator. Now, when you say rationalizing in math, what that means, that doesn't mean like it doesn't mean the same thing at all that it means in English, where you're trying to justify something to yourself. Rationalizing is to make it a rational number, and a rational number, right? You can see the word ratio in there, right? A rational number is something that can be written as a fraction of whole numbers. Now, a whole number is a rational number, and that's actually where we're going to be heading. We want to rewrite these fractions that we're going to be getting so that they don't have an I in the denominator. That's basically what that's going to end up meaning, because I is not a rational number. So let's take a look at one. Let's say I have 3 plus I over 4I. Now we're going to be asked to write these answers in standard form, okay? Just so you're aware of that. So we will have to be manipulating our answer to be what we want it to be. Now, the idea, though, is that we have to get rid of this I in the denominator. We don't want it there. It's actually, it makes it not rational. So we need just a real number down here. And so one of the rules of fractions, when you write things as a fraction, is whatever you multiply the numerator by, you need to multiply the denominator by the same thing. Well, and vice versa. Here, we want to get rid of I. What can you multiply I by to make it not an imaginary number? And the answer is itself. So what I'm going to do is I'm going to multiply top and bottom of this fraction by I. You want to remember that technically it's in parentheses, so you're going to have to distribute the I all the way across. So let's see what happens here. So if I distribute through the top, I get 3I, and then I squared, which is -1. So it's 3I minus 1. Down here, I get 4I squared, and I squared is -1, so this is now a -4. So that's kind of fun. Okay, my numerator is written in the wrong order. I need the real part to come first, then the imaginary part. So now this is -1 plus 3I. Notice I brought the subtraction moved to the front with the 1. And then I have a -4 down here. So what I can do is actually split this up over the denominator. So this denominator divides both of these numerators, both pieces of this numerator. So I have -1 over -4. And then over here I have plus 3I over -4. Now we need to massage this and simplify it a little bit. A negative divided by a negative is a positive, so this is positive 1/4 now. And then over here, I have a positive divided by a negative, and so that means it comes out negative, so I can write minus 3/4. And then the I is in the numerator, and so I can move it over here. And this is now in the standard form, right? Because it has, well, let me just write it over here. 1/4 minus 3/4 I. You have to be able to clearly identify what A and B are, right? So it needs to match up. So I can clearly see that A is 1/4 and B is -3/4. Right? So this is the form of the answer that you want. Okay, so that's when you have a pure imaginary number in the denominator, right? If it's a single term, all you have to do is just multiply by I. If there's no I down there, there's nothing to do, right? You just need to like massage it and get it into the standard form. So let's go ahead and take a look. There it is. Let's take a look at what happens to one of these when I have a binomial. I have a full complex number in the denominator. Okay, so let's say I have 3. In fact, I'll pull out 2 examples here. 3 over 3 plus I. And I'm going to pick another one over here. Let's do 5I over 2 plus 3I. Okay. Now, there's a problem. Most people want to go through and just multiply top and bottom by I again. But first, I'm going to show you why that doesn't work. First of all, if you're going to multiply by I on the top and the bottom, it has to distribute across 2 terms, right? So I get a 3I in the top, and if I distribute this I on the bottom, I get 3I plus, it's going to be minus because it's an I squared. 3I minus 1. And the problem is I still have an I in the denominator. Multiplying by I just kind of swapped the roles of the real and imaginary parts. So it didn't clear out that I. But it's a really strong temptation to do that because it seems like it should. And if you forget to distribute, it'll look like it should, but that's not what it does. So what we're going to do here is we're going to use that conjugate. One of the nice things about the conjugate is that it gives you a real number as a result. And that's what we're after. We want a real number in the denominator. So if I have 2 terms down there, I'm going to multiply by the conjugate of those terms. So let's see here. Oh, I already have it red. So what I'm going to do is multiply top and bottom by 3 minus I. Right? I'll just change the sign between them. And then we'll go from there. So in the numerator, I can distribute. I'll get 9 minus 3I. Oh, that looks beautiful. Now, the denominator, we're multiplying the difference of squares. We just saw a shortcut to multiplying complex numbers. All I have to do is square the first term and then square the second term and add them together. So squaring the first term gives me 9. And then the coefficient here is a 1. Squaring 1 gives me 1. So the denominator here is 9 plus 1. So now, let's see, I'm going to go ahead and swap this numerator around. So now this is minus, oh no, that's in the right order already. I don't need to swap anything. So I get 9 minus 3I over 10. And if I want to switch this to the standard form, what I do is I just split it up over this denominator. So this is 9/10 minus 3/10 I. And this is your final answer. So you do need to split it. If they're fractions, you still have to split it into 2 fractions. If you're lucky, they come out to whole numbers, but they don't always. Okay. Now, looking at the second one, now that you've seen one of them, and you've been looking at this second one, I'm thinking you probably have an idea of how to solve it already. So take a shot at it. Go ahead and pause the video here and see if you can work it out. And then once you have an answer, push play again. Okay, I'm going to assume you paused it here. And so let's go ahead and take a look. So what we're going to do, we have a binomial in the denominator, and it's complex. So that means I'm going to multiply by its conjugate. Right? The denominator I can actually handle first if I want. 2 times 2 is 4, and it's going to be plus. It's always a plus. And then 3 times 3 is 9, so it's 4 plus 9 in the denominator. If you're not sure, if you don't want to trust that formula, multiply it out. Just FOIL the whole thing out and see what you get. It should come out to the same answer. If you get the same answers both ways, you probably understand the shortcut. Okay, so that's the denominator. And then the numerator, let's see, 5i times 2 is going to be 10i. 5i times minus 3i. So it gives me a negative 15, but I'm squaring I, so that makes it plus 15. All right, so now I'm going to swap the numerator around and combine the denominator. That gives me that. And again, that's a pretty normal way to write a complex number, but we need to switch it to standard form. So we're gonna break it up. So it's 15 over 13 plus 10 over 13i. You are expected to reduce the fractions. So if either of those fractions reduce, you do need to go ahead and reduce those. Otherwise, you will end up with an answer getting marked wrong, even though it's numerically correct. So you do need to reduce your fractions. All right. Okay. So let's look at some of the other stuff that we're going to be taking a look at. Let's go ahead and clear that. All right, so the last couple things I want to take a look at is how to simplify more complicated expressions. So if I have something like this, square root of negative 49 plus the square root of negative 25, okay? First of all, here's my first piece of advice on any of these problems where we're just trying to simplify an expression with negatives in the square root. The first thing you want to do is pop all those i's out and rewrite it in terms of I. Right? So now with these, like I think you probably know the square root of 49 is 7 and the square root of 25 is 5. So you can certainly jump to that step as well. But I'm trying to separate these out so we're not doing too much at once. Because not all of them will be obvious. So we'll pull the negative out first. That gives me I times the square root of 49 plus I times the square root of 25. And so that means this is 7i plus 5i. And they're like terms, right? They're like radicals. They both have an I, so we can add them together. That gives me 12i. Right? And that's the simplification. And that is also in the standard form. Although I will point this out, every once in a while things get a little bit too nitpicky. Sometimes you are forced to write this, 0 plus 12i, because this is the real part and this is the imaginary part. So be aware of that. You may be asked for that 0 as well. Okay? And interestingly enough, some calculators, when they're dealing with complex numbers, will give you an answer. It'll say this. Because the way that they give the complex number, they give it like a coordinate where this is the real part and this is the imaginary part. Right? So be aware of that. Sometimes you plug that into your calculator, you'll take the square root of negative 1 and it tells you the answer is 0, 1. Right? And that doesn't really make sense unless you know this, that this is how they're giving it to you. Okay. So let's look at another one. Really, this is just order of operations with complex numbers at this point. Let's try this one here. How about 6 minus the square root of negative 7 squared? So, you know what? Take a minute. Go ahead and pause this and see what you get. right? And then we'll work it out together. So go ahead and pause. Okay, so there's a couple things here. One of the things I want to do, and I like to do, is just convert everything to the imaginary form first. So I can rewrite this now as 6 minus I times the square root of 7, and I'm squaring all of that, right? Okay, now we got to remember what that means to square a binomial. It doesn't mean square the 6, square I root 7. That is not what it means. What it means is to multiply this entire expression by itself. Right? So that means we have to FOIL it out. So we'll just go ahead and do that. 6 times 6 is 36. 6 times I root 7, negative I root 7 would be minus 6I root 7. And then let's see here. That's those two. Now we got this one. That's another minus 6I root 7. And then lastly, I have negative I times negative I, which gives me positive I squared. And then root 7 times root 7, which just gives me a 7. So that means that I'm just going to rewrite this so it's more clear. So that's 36 minus 6I root 7 minus 6I root 7. And that's an I squared, so that actually makes this minus 7. Right? Now we can just collect our like terms. 36 minus 7 is 29. And then here, the I root 7 is really kind of like the unit, right? Because that's all one radical piece. So what this ends up being is minus 12I root 7. Now, that's a pretty common way to write it. And it's my habit to write it this way. But if you are truly going to put it in standard form, the I has to come last. So this is 29 minus 12 root 7 times I. Now you want to make sure it does not look like I is inside that square root. We have to learn more things before we can take a square root of I, right? Because that's kind of, well, it's different. So in any case, this would be our final answer here in standard form. So it'd be 29 minus 12 root 7 I. All right, so let's look at another one here. Okay, so let's try this. Let's see what you can do with this one. So we want our answer in standard form. We'll do negative 15 plus 2 times the square root of negative 18 over 6. Now notice this looks a lot like something you would get out of the quadratic formula, doesn't it? So go ahead and pause it here, see what you can do with it. And remember, we want it in standard form, so that means the real part has to be in one place and the imaginary part comes second in that second place. Okay, so see what you can do with it. Alrighty, so I'm assuming you've paused at this point. So let's go ahead and do this. So the first thing I want to do, you know what, I can see there's going to be little busy work things going on in here. So I'm going to pull parts of this out and work on them in a scratch area. I'm just going to give myself a little scratch area here to work. So the first thing I have here is this square root of negative 18, right? Okay, so I know I can change that to I root 18, and that's 9 times 2 and 3 times 3. So that means that this is equal to 3I root 2. So that's what I'm going to put in for root negative 18. It's a really good idea to have a little scratch area because, well, quite honestly, it gets too messy if you put it all right where you're doing the next step. Okay, so we got there. We just simplified negative 18. Okay, now we can start multiplying some things out. So 3 times This is not a distribution across this. There's no plus sign in here. So it's just going to hit the 3 and stop. So 2 times 3 is 6. So that gives me negative 15 plus 6i root 2 over 6. Now that we're there, we can split this up over the fraction, right? So this is negative 15 sixths plus, in fact, I'm going to go ahead and pull that I out now, 6 root 2 over 6 times I, right? So we're looking at that. All we have to do now is simplify the two fractions that are here. So this first fraction, negative 15 sixths, can be simplified by 3. So if I divide by 3, top and bottom, so that gives me negative 5 halves. Over here in the second fraction, 6's cancel. So this is now plus the square root of 2i. So let me write that out neater. So it's negative 5 halves plus the square root of 2 times I. Now, that means that this is my real part, and this is my imaginary part, right? So you end up needing to separate it out and simplify. And, well, honestly, since we're going to be dealing with quadratics and stuff in the next lecture, you will be doing things like this. It will happen, right? There's arithmetic you have to handle. What is nice, one thing I do suggest is there's a lot of places where you end up doing the same steps over and over and over again, right? From one problem to the next. Look for ways you can shortcut that. Look for patterns that always seem to happen, right? And then ask yourself, will they always happen? Or is it just this example, right? Or is it just these examples? Because sometimes textbooks will do that to you, where they give you all the problems that have a certain property, and so you start thinking that's how the answers go, and it turns out that's not what they are. So you do want to play around with this a little bit and look for ways to make your arithmetic quicker, because that's what's going to slow you down, is your arithmetic. Because a lot of this stuff, I mean, quite honestly, if you got this far and you were doing something like completing the square, you've already done a lot of work to get that far. And then to simplify afterwards is another bunch of work, and it's kind of tedious. So you want to get a little more fluid at it. You want to get quicker at it, and you want to find things that you can do in your head if you can. Don't do anything in your head if you don't completely trust it, though. Write it down until you can trust your head. All right. Okay. So that concludes our lecture on complex numbers. They will come back up. There's a lot that goes on with the complex numbers. Trust me. As a matter of fact, you wouldn't be watching this video if we didn't understand complex numbers, right? Pretty much all of our electronics is based on it in one way or another. So it is pretty important. Any of you who plan to be engineers or anything like that, you're going to be probably better versed than I am with complex numbers by the time you're done. So in any case, until next time, guys, keep your pencils and your wits sharp.